Does every matrix, an n by n matrix, produce an eigenvector basis for Rn? Now, we already know the answer to this. It's no. Not every matrix will have built within it an eigenvector basis for Rn. The example we did in the previous video, there's a 2 by 2 matrix. I found that its eigenvalue had a multiplicity of 2, but there was only one basis vector for that eigenspace. There aren't enough vectors to form a basis for R2. In these cases, we say that the matrix is a defective matrix. So what are some conditions for the existence of an eigenvector basis? We would like some conditions on when you will be able to form an eigenvector basis. There's a nice result that deals with a very common case. We are not going to prove this. If we've got a set of eigenvectors v1 through to vr corresponding to real, distinct, so different from each other, eigenvalues 1 through to r, it will turn out that that set of eigenvectors v1 through to vr is linearly independent. It's going to be the case very often that we will get a matrix that has distinct eigenvalues and enough of them. And so this is what's known as proposition 4.2-8 in your textbook. If an n by n matrix has n distinct real eigenvalues, then it will turn out by the above that the set of eigenvectors, they will have to be linearly independent. Then it's going to have an eigenvector basis for Rn. And that really just piggybacks off this result here. Now, this is not an all-encompassing result, but this is a very common case. Now, we already looked at this in the very first video for today. Here was a 2 by 2 matrix. We found that its eigenvalues were 1 and 5. We found that each one of these eigenvalues produced a one-dimensional eigenspace, and that means that this set here was a basis for R2. If I have a 2 by 2 matrix, I shouldn't expect any one of my eigenspaces to be 7-dimensional or 12-dimensional. Remember, the dimension of an eigenspace has to be less than or equal to the multiplicity of that root, and that has to be less than or equal to n. Your eigenspaces can't be bigger than the dimension of the space that they are in. Now, in this previous example, with this 3 by 3 matrix, we found lambda 1 and lambda 2, the dimension of this null space corresponding to this eigenvalue had to be 1. We found that the dimension of the eigenspace corresponding to these guys had to be 2. E1 had a basis, -2, 1, 1. E2, so what should I make of this result? Now note, if we take any of the vectors from E1, they're going to be linearly independent when we put them into a set with the basis vectors in E2. That was according to that theorem. So if we call this B1 and we call this B2 and B3, by the null space properties, this set B2 and B3 are independent. And that means that A does have an eigenvector basis for R3. We take all of the eigenspaces and we take their basis vectors and we put them together. So when we take into account the dimensions of all of these spaces, it adds up to 3, and that forms our eigenvector basis for R3.